September 15th, 2006. EasyJet Flight 6074. 144 people. Over France. A loud clunk. Then darkness. Captain's instruments. Gone. Autopilot. Gone. Radios. Gone. Transponder. Gone. An Airbus A319, invisible to every radar screen. An American Airlines 777 crossed its path 19 seconds later, 600 feet below. TCAS blind on both planes. The part that caused this had been rejected from 3 aircraft, repaired 4 times, returned every time. 3 words: no fault found. How does a part that fails 4 times end up on a 5th plane? To answer that, we need to go back 2 days, to a maintenance hangar at London Stansted, a replacement part pulled from a shelf, and a series of decisions that, one by one, stripped away every layer of protection between 144 people, and the most complex electrical failure an A320 series aircraft had ever experienced. Because the story of Flight 6074 isn't really about a broken component. It's about a system that was told, repeatedly, that something was wrong, and repeatedly decided that everything was fine. The part tried to warn them. 4 aircraft, 4 removals, 4 chances, and 4 times, the same 3 words came back: no fault found. By the time those words reached the 5th aircraft, there was nothing left between a routine flight and a mid-air collision, but 19 seconds, and the instinct of one air traffic controller who decided to trust his gut over his blank radar screen. The aircraft at the center of this story was an Airbus A319, registration Golf Echo Zulu Alpha Charlie. Brand new, manufactured in February of 2006, just 7 months before the incident. Powered by 2 CFM56 engines, a member of the A320 family, which meant it was fly-by-wire. Every flight control input passed through computers before reaching the control surfaces. That design makes the aircraft remarkably safe and precise. It also makes it entirely dependent on electricity. Without electrical power, an Airbus doesn't just lose its instruments, it loses its ability to fly like an Airbus. Despite being only months old, Golf Echo Zulu Alpha Charlie had already built a troubling maintenance history. 10 electrical system problems in the month before the incident alone. Generators tripping offline, control units faulting, power interruptions that came and went without explanation. Many of these issues traced back to a known industry problem, a bad batch of memory chips inside the generator control units, affecting a 320 family aircraft built during that period. The chips caused intermittent failures. Generators would trip off, get reset, and work fine for a while. It was a known nuisance. Mechanics had seen it before, and that familiarity would prove dangerous because it gave everyone a comfortable explanation for symptoms that actually had a different cause entirely. On the night of September 14th, 2006, the aircraft was parked at Stansted after its number 1 generator had tripped offline during a flight. EasyJet mechanics replaced the number 1 generator control unit, the GCU, a shoebox-sized computer responsible for monitoring the generator's output, regulating its voltage, and activating protective functions if something goes wrong. They pulled a replacement unit from stock, installed it, and ran a ground test. The generator tripped off again immediately. Best practice at that point was clear: reject the new unit. If a replacement part fails right out of the box, something is wrong with the part, not the aircraft. But the mechanics assumed this was just another instance of the known memory chip issue. They reset the generator. It held. They signed off the aircraft as serviceable. What no one at Stansted knew, what no one anywhere knew, was that this particular GCU had already been installed on 3 different aircraft in the previous 5 months. Each time, it had caused a malfunction. Each time, it had been removed and sent to the manufacturer, Hamilton Sundstrand, for testing and repair. And each time, Hamilton Sundstrand's engineers had run their bench tests, failed to reproduce the fault, and stamped the paperwork with 3 words: no fault found. The unit went back on the shelf, back into the supply chain, back onto the next aircraft. This wasn't unique to this one unit. Across the industry, roughly 29% of GCUs sent to Hamilton Sundstrand for repair were returned unmodified after engineers failed to reproduce the reported fault. There was no system in place to flag a unit that kept coming back. No database tracking how many times the same serial number had been rejected from service. No threshold that said, if a part fails this many times, stop putting it on airplanes. The information existed, scattered across 4 maintenance logs on 4 different aircraft, but no one had connected the dots. The morning of September 15th, Golf Echo Zulu Alpha Charlie departed Stansted for Alicante, Spain, with a different crew. About 20 minutes into the flight, the pilots heard a sound, a distinct clunk from somewhere inside the aircraft's systems. The number 1 generator had tripped offline. The ECAM displayed the fault. The crew attempted a reset. It didn't work. So they followed the checklist, turned off the failed generator, started the auxiliary power unit, a small turbine engine in the tail that can substitute as an electrical source, and let the APU power the left electrical network for the rest of the flight. They contacted EasyJet Maintenance, who advised them to continue to Alicante. Under the minimum equipment list, the aircraft was legal to fly with 1 generator inoperative, provided the APU stayed running and the cruising altitude didn't exceed flight level 335. The clunk was noted, the failure was logged, the flight continued. In Alicante, a crew change took place. The pilots scheduled for the return leg, Flight 6074 back to Bristol, arrived and walked over to their aircraft. The captain was 42 years old, with roughly 8,800 hours of total flying time, though he had only recently transitioned to the A320 family and had logged just 393 hours on type. His first officer was 34, with 3,200 hours total and 560 on the Airbus. Neither was deeply experienced on this aircraft. They spoke briefly with the outbound captain, who explained the generator failure and how the crew had handled it. Based on that conversation and a review of the minimum equipment list, the new crew accepted the aircraft. The captain filed a flight plan for flight level 320, below the MEL ceiling, and requested extra fuel to account for the APU running throughout the flight. In the cockpit, the crew completed the standard pre-flight checks plus the special MEL procedures, verifying the APU was powering the left network, confirming system indications were normal, checking warning lights. Everything appeared to be working. Outside, 138 passengers boarded a gleaming aircraft that was, on paper, perfectly safe to fly. The cabin crew closed the doors. Total on board, 144. At 9:26 UTC, EasyJet Flight 6074 pushed back, started engines, and taxied out under a bright, cloudless Spanish sky. The captain flew. The first officer monitored. They climbed west over the Mediterranean coast, then turned north across Spain and into French airspace, settling into cruise at 32,000 feet. For the first hour, the flight was unremarkable. The APU hummed in the tail. The electrical system fed both networks as designed. Coffee was poured. The French countryside passed below in early autumn sunlight. To understand what happened next, you need to know one thing about how the Airbus A319's electrical system protects itself. The generator control unit doesn't just regulate the generator. It also monitors for dangerous conditions. One of those is called welded protection. When a generator is turned off, no current should be flowing through its distribution line. If the GCU's sensor detects current anyway, it assumes the worst, that a switch called the generator line contactor has failed to open and electricity from another source is backflowing into the dead generator, which could damage it. So the GCU responds by opening a different switch, the bus tie contactor, to completely isolate the entire left network from any power source. It's a drastic measure, but it's designed for a real emergency. The problem is, what happens when the sensor is wrong? Inside the GCU, installed on Golf Echo Zulu Alpha Charlie, a single pair of electrical contacts in one sensor was defective. These contacts were supposed to close when current was flowing and open when it wasn't. But intermittently, sometimes, not always, not predictably, they did the opposite. When the generator was on, the contacts would occasionally stick open, making the sensor read no current where current existed, which triggered a different protection and tripped the generator offline. That's what had happened on the 3 previous aircraft. That's what had happened on the outbound flight that morning, the clunk the earlier crew had heard. But there was a second failure mode, and it was far worse. When the generator was off, those same contacts could sometimes close, making the sensor report current that wasn't there. And that would trigger the welded protection, which wouldn't just trip the generator, it would isolate the entire left electrical network. At 10:52 UTC, Flight 6074 was passing over northwestern France near Nantes, under the control of the Brest Area Control Center. The autopilot was engaged. The auto thrust was set. The flight was 85 minutes old and roughly halfway to Bristol. And then the crew heard a sound they recognized, the same clunk the previous crew had described. Same aircraft, same system. But this time, the consequences were catastrophic. The defective sensor contacts had closed with the generator off, reporting a phantom current. The GCU activated its welded protection and commanded the number 1 bus tie contactor to open. In an instant, the APU, which had been faithfully powering the left network for nearly 2 hours, was severed from AC Bus 1. The left network went dark. And because a C Bus 1 feeds the AC Essential Bus, and because on this generation of A319, the transfer to the backup was not automatic, but required a manual button press by the pilots, the Essential Bus went dark too. The cascade was immediate and overwhelming. The captain's primary flight display and navigation display went black. The upper ECAM screen died. The autopilot disconnected with a master warning chime. The auto thrust dropped offline with a master caution. Most of the indicator lights on the overhead panel, the lights that tell pilots which systems are on, off, or faulted, simply disappeared. In the passenger cabin, 138 people felt nothing unusual. But in the cockpit, the 2 pilots were staring at an instrument panel that had just lost over 100 systems simultaneously. The full list of failures ran 3 pages long. If you want to support this channel and help us keep telling these stories, take a moment to like this video and subscribe. It makes a real difference. Now, back to that cockpit over France. The captain's immediate instinct was right. Something had cut power to the left network. His initial guess, that the APU had failed, was wrong, but it was a reasonable assumption. He couldn't see the real cause because the indicator lights that would have told him what had actually happened were themselves unpowered. He handed the controls to the first officer, whose instruments on the right side were still working off the number 2 network. The first officer took over manually. No autopilot, no auto thrust, no flight director, flying an alternate law, which meant the normal fly-by-wire envelope protections were gone. At 32,000 feet, hand-flying an A319 in alternate law, while your captain tries to decipher an avalanche of failures beside you, is not a scenario any training syllabus covers. The captain turned to the ECAM. The lower screen was still alive, powered by AC Bus 2. It displayed a wall of warnings and caution messages. Among them was the critical instruction: ELECACESSBUSFAULT, ACESSFEED, select ALTN. This was the one action that could have restored power to the Essential Bus by switching its feed from the dead AC Bus 1 to the working AC Bus 2. One button press. Airbus estimated it would take about 1 minute. The captain looked up at the overhead panel to find the ACESS feed push-button selector. Neither of its 2 caption lights, fault and ALTN, was illuminated. He pressed it anyway. Nothing happened. He pressed it again. Nothing. The electrical system did not reconfigure. The button didn't change position in any way he could verify. It depressed by barely a millimeter, with no visual feedback, no click, no confirmation. The caption lights stayed dark. He had no way to know if he'd pressed it correctly, pressed it twice by accident, or if the button itself had failed for reasons entirely separate from the electrical collapse. Investigators would later test the button on the ground. It worked perfectly. They never determined why it didn't work in flight. That button was the last line of defense between a manageable single-generator dispatch and the total electrical blackout that was now unfolding. Airbus had designed the system assuming the crew would press it within 60 seconds of the failure. They had not designed for the possibility that the crew couldn't. With the Essential Bus dead and no way to revive it, the captain shifted to communication, the third priority after aviate and navigate. He reached for his radio management panel. The lights were gone. He tried VHF Radio 1. No response. VHF Radio 2. No response. He declared Mayday on the emergency frequency, 121.5 megahertz. Silence. The first officer tried from his side. Nothing. The captain switched to audio control panel 3. Still nothing. 3 VHF radios existed on the aircraft. All 3 were technically powered by the right side network and should have worked. But all 3 audio control panels, the interfaces that let pilots actually select and use those radios, drew their power from the DC essential bus, which was dead. 3 working radios, 0 ways to use them. A redundancy that looked robust on paper had been defeated by a single shared dependency that no one had fully accounted for. The aircraft was now flying at 32,000 feet over France, with no radio contact and no transponder signal. To every radar screen at the Brest Control Center, EasyJet Flight 6074 had simply vanished. At the Brest facility, a controller noticed the disappearance within moments. He tried calling the aircraft. Once, twice, 3 times. No reply. He contacted other frequencies. He asked another EasyJet flight to relay. He tried the emergency frequency. Nothing came back. The control room began filling with a sickening possibility that Flight 6074 had crashed. A shift change was minutes away. The atmosphere was tense. And then, into that silence, an American Airlines Boeing 777 checked in, westbound at flight level 320, the same altitude as the missing EasyJet. The controller's mind made the calculation instantly. If Flight 6074 was still airborne at its last known speed and heading, it was now somewhere ahead of the American Airlines flight, possibly directly ahead. He asked the 777 crew to check their TCAS, the traffic collision avoidance system that detects nearby aircraft by interrogating their transponders. The American crew checked. Nothing. Their TCAS screen was clean. And it would be, because TCAS requires a transponder signal from the target aircraft to function, and the EasyJet's transponder had been dark for 10 minutes. 2 aircraft converging at a combined closing speed of over 1,000 miles per hour, and the system designed to prevent exactly this scenario was completely blind. The controller made a decision that would later be credited with preventing a catastrophe. He ordered American Airlines Flight 63 to descend immediately to flight level 310. He didn't know for certain the EasyJet was still flying. He didn't have radar confirmation. He had a blank screen and an instinct. The American crew complied. They descended, and moments later they reported seeing an aircraft pass overhead, an EasyJet, crossing their path from left to right, 600 feet above. Investigators later calculated the geometry. The 2 aircraft crossed the same point in space 19 seconds apart. American Airlines 63 had reached approximately flight level 310 at the intersection point, 600 feet below the EasyJet at 320. At the closest recorded moment, the horizontal separation was 2.67 nautical miles. If the controller had not ordered the descent, if both aircraft had remained at flight level 320, they would have passed through the same coordinates less than 20 seconds apart at the same altitude with 0 electronic warning on either flight deck. The margin between a serious incident and the worst mid-air collision since Überlingen was a single controller's decision to act on incomplete information. Back in the cockpit of Flight 6074, the crew had no idea any of this had happened. They didn't know they'd been invisible. They didn't know they'd nearly hit another aircraft. They were focused on keeping their own plane flying. About 10 minutes after the initial failure, the captain worked his way through the lower priority ECAM items and reached the instruction to switch from transponder 1 to transponder 2. He made the switch. The control panel was still dark, but the squawk code digits reappeared. Not knowing if anyone could actually see the signal, he selected 7700, the universal emergency code. It was the best he could do. On the ground at Brest, the secondary radar return bloomed back onto the screen. Squawking, 7700. EasyJet 6074 was alive. The relief was immense, but so was the alarm at how close the 2 aircraft had come. The captain reviewed what was left. The list of working systems was far shorter than the list of failures. He tried resetting the APU, shutdown, restart. No effect on the electrical system. He tried turning the number 1 generator on, then off. Nothing. He pressed the ACESS feed button again. Still nothing. The aircraft's left network was gone and was not coming back. He then faced the decision that would define the rest of the flight: where to land. The crew's first instinct was to divert to the nearest airport, but the captain's reasoning against it was sharp and layered. Without radios, any deviation from the filed flight plan could be interpreted as a hostile act. This was 2006, 5 years after September 11th, and the threat of military interception was real. Without working communications, they couldn't coordinate with a diversion airport, couldn't receive weather, couldn't get approach clearances. They had the Bristol weather from before departure: good visibility, light winds, adequate runway length even with degraded braking. They had a programmed arrival in the flight management system, and sticking to the flight plan was the standard procedure for total radio failure. It kept the aircraft predictable, allowing controllers to clear a path. The captain made the call: continue to Bristol. The first officer flew the entire route by hand. No autopilot, no auto thrust, alternate law, manual thrust. While the captain managed systems, ran checklists, and briefed the cabin crew. He gave a NITS briefing: nature of the problem, intentions, time to landing, special procedures. He made a passenger announcement. He tried calling Bristol ATC on his mobile phone during the descent. 2 handsets, multiple attempts, none connected. Bristol ATC knew the aircraft was coming. Brest had passed the word. West Drayton had related. The transponder was painting 7700 on every scope in southern England. Controllers cleared the airspace around Bristol, sequenced the aircraft in, and positioned fire crews on the ground. They broadcast wind and landing clearance in blind, hoping the pilots might hear. They didn't. On approach, the captain selected flaps. They deployed normally, a small mercy. He selected landing gear down. No indicator lights, no sound of extension. The gear hadn't moved. The landing gear safety valve, which prevents deployment above a certain airspeed, had lost its airspeed data along with the left electrical network and had defaulted to closed. The captain reached for the emergency gear extension handle and lowered the gear by gravity. 3 green lights. No. The indicators were dead too, but the gear was down. They had to trust the mechanism. The first officer flew the ILS approach on his instruments, the only set still working in the cockpit. Full flap, manual thrust, no flight director. He put the aircraft on the runway at Bristol. Heavy braking. The aircraft stopped quickly. The captain taxied to the stand. He selected the engine master switches to off. The engines kept running. The shutdown command, apparently, also depended on something powered by the dead left network. The captain pulled the engine fire shutoff handles. The engines finally spooled down. All 144 people walked off the aircraft. When investigators from the Air Accidents Investigation Branch examined Golf Echo Zulu Alpha Charlie, they couldn't initially get the aircraft to power up normally. Numerous abnormal indications persisted until they replaced the number 1 generator control unit. Extensive testing eventually traced the root cause to a single defective contact in one sensor inside that GCU. A contact that intermittently opened when it should have been closed and closed when it should have been open. The same contact that had likely caused the failures on 3 previous aircraft. The same contact that Hamilton-Sundstrand's bench tests had failed to detect 4 times. The investigation reached beyond the cockpit into the maintenance ecosystem that had allowed this to happen. The GCU had been removed from 3 aircraft in 5 months, sent for repair each time, and returned each time with the notation, "No fault found." Hamilton-Sundstrand had no procedure to flag units with excessive rejection rates. No database tracked serial numbers across multiple removals. No threshold existed that would pull a recurrently failing unit from the supply chain. 29% of all GCUs sent for repair came back unmodified. The part wasn't just defective, it was trapped in a loop, cycling through the fleet until it landed on an aircraft that had no redundancy left to absorb its failure. The AAIB also examined why the failure was so devastating. The answer lay in the electrical system's design. On this generation of A319, the transfer of essential bus power from AC Bus 1 to AC Bus 2 required a manual button press. Newer Airbus models had already automated this transfer. On the older aircraft, the assumption was that crew would act within 60 seconds. Nobody had fully analyzed what would happen if the crew couldn't. if the button failed, if the captions were dark, if the pilots were drowning in 100 simultaneous warnings, with no way to verify which switch was in which position. The certification analysis had categorized the loss of all VHF radios as major. The AAIB argued it should have been hazardous, one category below catastrophic, given that total radio and transponder loss in controlled airspace could lead directly to a mid-air collision, as it nearly had. The AAIB found that the aircraft's 3 VHF radios were technically on separate power networks, but all 3 audio control panels, the units that let pilots actually use those radios, depended on a single bus, the DC Essential. When that bus died, 3 radios became 3 useless boxes. A redundancy designed on paper had a single point of failure hidden in the architecture. The same pattern repeated across multiple systems. Sensors, indicators, protections that looked independent on the schematic, but shared a common vulnerability that only revealed itself when the essential bus went dark. The investigation issued 14 safety recommendations. Airbus was directed to modify the A320 series electrical system to automate the AC essential bus transfer, removing the manual button from the critical path entirely. Hamilton Sundstrand was told to implement tracking systems for units with excessive rejection rates, ensuring that a part returned "no fault found" multiple times would be flagged, investigated further, or permanently removed from service. The GCU logic was redesigned to require multiple sensors to agree before activating the welded protection, so a single defective contact could no longer isolate an entire electrical network. The VHF radio power architecture was modified to prevent all 3 audio control panels from depending on the same bus, and the AAIB recommended that EASA and the FAA recategorize the total loss of radio communications on a transport aircraft from major to hazardous. The clunk that the outbound crew heard over the English Channel that morning was the differential protection, the GCU's sensor reading no current when current was there, tripping the generator offline. A nuisance, a known issue, easily managed. The clunk that Flight 6074's crew heard over Nantes 85 minutes later was the welded protection, the same sensor, the same defective contact, but reading a phantom current with the generator off, isolating the entire network. Same sound, same part, entirely different catastrophe. The first clunk took away a generator, the second clunk took away the airplane. Golf Echo Zulu Alpha Charlie was 7 months old and had already experienced 10 electrical faults in a single month. The GCU installed in its belly had been rejected from 3 aircraft in 5 months. Every piece of information needed to prevent what happened on September 15th existed somewhere. In a maintenance log at Stansted, in a repair order at Hamilton Sundstrand, in a tech log entry in Alicante. But no system required anyone to read them all together. The data was there. The pattern was there, and 3 words, "no fault found," had become a stamp that turned a warning into a clearance, every single time. The next time a component is pulled from an aircraft, sent for testing, and returned with those 3 words on the paperwork, someone now has to ask a question that didn't exist before Flight 6074. How many times has this happened before? That question exists because 144 people flew across France in an invisible airplane, 19 seconds from a collision that no one would have seen coming, and because one air traffic controller, staring at a blank radar screen, decided that a missing plane might still be worth saving. If you found this story worth telling, subscribe and turn on notifications so you don't miss what comes next. And if you want to hear about the time a brand new aircraft's flight controls locked up at the worst possible moment, because of a design choice the manufacturer knew about and chose not to fix, that story is waiting for you right here.